Hello there, thank you for joining me again today. On the bench is let's step back in time to Cold War, back in the nuclear threat age of the Cold War, and today we're going to be looking at two parts of that horrific time of living through the Cold War. We've got some Cold War communications equipment here that are actually retrieved from a nuclear bunker, which was used by government officials in the event of a nuclear war with the former Soviet Union. These radios were installed quite widely across the UK into nuclear bunkers, along with other models of PYE and Philips radios that we'll also look at on this channel a bit later on. So we're going to have a look at that, strip it down, go inside, look at the theory of operation. These are crystalled radios as well, not synthesized. No surface mount rubbish in these. You know, nuclear bomb proof in many ways, and built for that era. So we're going to have a look at some 1970s, 1960s, 70s electronics, radio transceivers. There's two here. Both of these are PYE Westminsters. We've also got dosimeter here, which I'm going to show being set up, calibrated, and we're going to discuss units of radiation measure, the sievert, the grey and the rentgens. And we've got a dosimeter here which is charged and calibrated by this charger unit, and I'll show that working as well. And we'll talk about radiation exposure, and we can obviously look at how units of radiation can affect the human body, as described in the Nuclear War Survival Skills book, which is a book primarily written by Oak Ridge National Laboratory in the United States, which is responsible for nuclear weapons testing in the United States. This book was actually forwarded by Dr. Edward Teller, and for those who don't know who Dr. Edward Teller is, he was the nuclear physicist which designed the hydrogen bomb, or what's known as a thermonuclear nuclear weapon, which is in today's arsenals, which superseded the standard atomic bombs which were dropped on Hiroshima and Nagasaki in the Second World War. And after he designed that bomb, which was 1,000 times more powerful like for like than any previous nuclear weapon ever used on Japan, for example, he then forwarded this book to help Americans understand how to survive a nuclear war from his standpoint, as well as Oak Ridge National Laboratory's standpoint. And it goes into great depths in there about nuclear radiation fallout and the different types of nuclear radiation, being gamma, alpha, beta, etc., cesium and strontium, and various other isotopes that come from a thermonuclear explosion, and its effects on the thyroid and the cellular and DNA level of the body. So we'll talk about that as well at the back end of the video when we look at the dosimeter and how its unit of radioactive measure versus time is measured, and the charge unit. We'll strip that down and have a look at that as well. So it's going to be a good video. We'll get right into it, so stay with me and sit back and enjoy. Okay, so we've got the radio apart now. The cases that are on them are very heavy steel, very heavy. I mean, quite thick, copper steel. You can't bend them. You know what I mean? They are literally bomb-proof. Extremely, you know, thick metal as well. And they're held in with these little retainer screws as well on these little spring clips here, which you can see these little spring clips, and the screw locks into that, which is a brilliant idea, really. I always like PYE stuff, you know. They made proper radios in my view. Did PYE, Philips and Simoco before it became, I think, what is now the modern version of it, which is Supura. And Supura now make Tetra radio equipment for what is the digital radio networks of today. And naturally a direct competitor to Motorola, etc., were the big players in the world market, but they've still got a significant foothold in the UK and other markets around the world of Supura. Now, as far as PYE was concerned, PYE used to make all kinds of radio equipment. and I've actually got quite a large collection of PYE radio equipment myself, but there's a lot of gear out there still that you can pick up quite cheaply from radio amateur rallies and car boot sales and things like that. I do often see it, so I tend to, depending on how much it is, I will buy it. But if we just have a look inside this radio, this being the front panel part of it, that plugs into the controller, which I'll, if I can get the controller out of the box, wherever it is, I'll connect it up and show it working. But basically you've got your power on the front right here, that's where the power connects in, and then you've basically got 2 antenna sockets. Now these effectively would use either a duplexer connected to the both antenna sockets. One will be receive, one will be transmit, or alternatively you could have 2 separate antennas separated on a radio tower. You've also got a transmit test button there, which is a momentary button, and then this connector here goes off to your controller as per what it says here. But it's quite basic at the front. It's got the slip down lid as well, and it's a PYE Westminster model. Now internally, it's on both sides, there's a radio section, but internally, if we just zip it round so we can have a look internally. So what we've got here, on this side here, we've got the coaxial cable which goes to the one of the antenna sockets on the front. In this case it will be the, looks like possibly the receive side on this side, and then the transmit side on the other, but we'll look at that in more detail in a moment. But we've got some kind of what looks to be an RF amplifier section with the look of it, because it's got power. So this could be the transmitter power amplifier stage, which I think it is, and this has obviously got power in it. It could also be the front end mixer stage as well, but we'll have a look at that. But with it having DC power on it, it's quite likely it could be the transmit multiplier and final output RF amplifier for the transmitter. But we'll just flip it over and have a look. These radios were crystal radios. Oh no, I think it was the this is a transmitter section. Yes, that's a transmitter. So I think that's the, this is a receiver front end. This is the other side to the module on the top there, this section here. So I think this is the RF front end for the receiver, comes in. These are the amplifier stages, mixer. I think that's the local oscillator input, and that will be the IF output. So you get the RF coming in there from the antenna, amplification and filtering with the tunable helical resonators, and then obviously then multi-stage amplifier mixer with the local oscillator input from what will be the local oscillator generator PCB, and then obviously then the local oscillator mixed with the incoming RF from the antenna socket produces what's an IF, an intermediate frequency, probably at 21.4 megahertz or 10.7 or something, coming out of here then to be amplified up and then demodulated and naturally passed off then for squelch and audio processing then to the speaker. Now looking at this front end section here, which continues through underneath here, these helical resonators are tuned to get the maximum Q on the frequency that you're using it on. So you would set up a signal generator, radio test set to generate X signal at X level, and then you would then basically tune these resonators to get the best signal to noise and distortion out of the measurement. If you watch my other videos, you'll see how to do that as well, but this is basically a mechanical tuning. Of course, in modern day radios today, they use varactor diodes, which are variable capacitance diodes, in place of what are physical movable helical resonators or cavities. You tend to find at VHF frequencies use helical resonators, which are coils of wire wrapped round a former and then a slug in between, which is adjustable, and then obviously that Q can be tuned in the VHF band. On UHF it tends to be cavity oscillators, so basically it's a couple of turns of wire onto the input and output with a dividing chamber with a cut through in it, and then you have a mechanical slug that then tunes the physical dimensions of the cavity to then give it an RF filter characteristic. But here we've got good old-fashioned, you know, this will be made out of brass, tin plated brass, I think, you know, built to last. And obviously this is a crystalled radio, so it's not a synthesized radio like modern radios are, where they have a microcomputer, a voltage controlled oscillator and a synthesizer in order to generate the transmit and receive frequencies. This uses quartz crystals, and they go in the sockets here, and you can have up to, you know, probably 10 channels. I think there's 10 sockets in total, 10 for transmit, 10 for receive. And you would net the crystals as well when they were put in, so naturally this side is a transmitter side, this section. So we've obviously got a, you know, a microphone amplifier stage, I think, at the end there. The input audio signals are fed in. If you look a bit further here, we start with a multiplier, so we've got the crystals running at very low frequency when they're in, and then these are multiplied up, and that's what these are, these sections. These are multipliers, and so the multipliers take the second harmonic typically of the fundamental frequency and then double it, and so therefore, you know, you get multiplication from a low frequency from the crystal right the way up, finishing at the desired frequency that we want out. And that's then passed to what is an exciter. I think this transistor, if it's a transistor, it is, that transistor there is the final exciter. That's a final drive output then, so many 100 milliwatts or whatever drive to this RF power amplifier section. So this then amplifies up the final low level signal that's left this board into what is the transmitted output via a coaxial relay that switches between transmit and receive or whatever. I think this is not a relay, come to think of it. I think this is another filter, and I think when we flip it over on the other side we'll see the slugs for this, because it's an in and an out. So that's the output of the transmitter power amplifier, goes through another filter and then fed off to this antenna socket here to the transmitter. So again, when you're choosing a transmitter crystal, it wouldn't be the frequency of the output. It would say there's a mathematical equation that you did to calculate the crystal frequency with the multiplication factor of the doublers, which are employed to double the signal and multiply it up, and that would then equal an output at the right frequency. So to be really careful at calculating your frequencies and your crystals. And there was a company called in the UK High-Q Crystal Company, Magnite. There were quite a few about in the early part of my career where you ordered your crystals from, and they could take some time to make as well. You know, it weren't like overnight delivery. You had to calculate the frequency. In the service manual for the radio, it told you how to do that, how to calculate the frequency of the crystals with a multiplication factor, the multiplier, to get you the desired output frequency. Now what you have to be really careful on as well on the receiver section, and I made this mistake quite a lot myself as an apprentice radio engineer, is that when you did the receive crystals, which are here, you had to also take into account the intermediate frequency as well as the receiver, which is the local oscillator. And so if you ordered the same frequency crystal as the transmit one and assumed it would be the same, you'd be in for a big surprise, because it wouldn't work, because the receive crystal was for the local oscillator, and the local oscillator had to run high or low of a desired input frequency from the antenna to produce the desired IF output frequency. So for example, if you wanted you know, to receive, I don't know, 160.7 megahertz antenna signal coming in, that's the desired radio frequency you're wanting to receive, you would order a crystal after taking into account of all the multipliers and everything, so that the output frequency into this socket here for the local oscillator, for the mixer, will be 150 megahertz dead. And that way then, when you put in 150 megahertz in here, and you've got 160.7 megahertz coming in on here, the difference between those two is 10.7 megahertz here, and that would then be your IF, and that would then allow the receiver to receive that signal and obviously demodulate it, and then you would ultimately receive that channel or frequency. So again, you had to be very careful at calculating the frequencies of the crystals, and you adjusted the multipliers up so that again, without breaking the cores could be broken quite easily, so you used to use methylated spirits and things like that in order to try and free off the grease that they used to put on the ferrite cores inside these, and it was so easy to crack them and break them, and I did that so many times over the years. And you had to soften up the like, it was a grease that they put on the ferrite slug to try and stop it from just turning out. It had like a piece of like a nylon tape sometimes as well, a white striped nylon tape that went through the core against the threads, and if you twisted it too quick with a trimming tool, oh, that were it, it just used to go crack and all the ferrite dust would break off, and it used to get into the threads and it would smash all the cores up, and you used to have a lot of swearing going on in the workshop when that happened. It used to be a nightmare problem. And of course, you know, tuning these up, it used to be done by current a lot of the time in the manual, because a lot of radio workshops couldn't afford the advanced spectrum analyzers that were just coming out at the time. They were extremely expensive. So tuning up a multiplier stage today, of course, is dead easy using a spectrum analyzer, but back then you couldn't, you know, many people couldn't afford that, even in business. So the way they did it was that in the manual it used to ask you to measure the current going to the multiplier board, and so you would tune up the cores to get the maximum current, because that's when the RF amplifier stages were obviously amplifying at the maximum on whatever output frequency that you've got. And of course they were very clever in doing the adjustment procedure on it, and it used to be quite an involved process of adjusting up the multipliers to get the right frequency output. And if you didn't do the alignment procedure right, it were a nightmare. You know, you used to have to start right back at the beginning again and go through these lengthy procedures on how to tune each core up to get the right frequency output as well. But basically the architecture is quite simple here. We've obviously got the what is the front end here with all the amplifiers in, and as I described earlier, the cavity tuning to tune out unwanted, undesired out of band radio frequencies. Then with a mixer, a local oscillator input, and then an output, an IF output, which is then fed off, it looks like, to this board here. And as we can see, we've got an ITT IF filter, so we have to filter it again, and it is 10.7 megahertz as it says there. So the local oscillator output is fed in here, that goes through the filter. I think there's an amplifier transistor down there as well, I think, yeah, some transistor. So that amplifies up the IF signal. Then we've got again more pre-selectors after it to clean up the output that's coming out the filter. And then we've got some more amplification going on down there, which is those transistors with they look like jelly beans. And then we've got an output then to another filter, which is this. So we'll have as you can see here, another local oscillator to produce a second IF. And this is a crystal here where my finger is, and this then produces another IF to mix here with the IF of 10.7, and then that produces, say, 455 kilohertz second IF, which is via this filter. So anything coming in here that's not 455 kilohertz is rejected through the filter, and only 455 kilohertz leaves the filter, which is then sent into what is the discriminator board. So that's what this is. This is a demodulator board. Now in the early days, of course, before ICs that came available that were FM discriminators in a chip, or AM demodulators, in these early times ICs weren't commonly available, and obviously the way that the FM process for demodulating an FM signal was done through using direct discrete individual components to produce a circuit which would ultimately then pull off the audio content. A lot of it was done through ring diodes and the process of stripping off the audio content from the 455 kHz IF, and that was then the frequency modulated content. So this board is basically what would be absorbed into one IC now, one little chip, which is used in most of the modern radio receivers. And I think I can show you an example of that now, actually, because I have a 934 megahertz radio, which does have that kind of architecture in it, believe it or not, when I can get it out. So again, to compare it against a modern radio, this is a 934 megahertz synthesized radio. This essentially, this section here is what is this section on the old radio, but we can see here that we move to a discriminator chip, which is down here. This IC here is the demodulator IC, and so basically this chip does everything that's on that entire board. So that entire board is just basically absorbed into that IC where my thumb is, and that's basically it. That's why miniaturization became possible, is because obviously we took the discrete element away from using large scale processing in order to get what we wanted, and then miniaturized it into an IC. And you can see the filters as well are much smaller now, tiny little filters in comparison to the big chunky size filters that we see in modern radio equipment as well. And there are further advances than this now, obviously, in software defined radio, SDR, that kind of technology. Then again as well, after we process the audio output from the receiver, then we naturally then have to send that into pre-emphasis and de-emphasis circuits, squelch circuits, to have a noise squelch so that we're not listening to white noise when there's no radio signal present. And again, this is the other side of the TX filter we were talking about on the other side, the transmitter filter. It has two tunable slugs, so we tune the transmit there because it pokes through to this side. But the output of this audio content is fed by this transformer here, and this transformer naturally is a balanced to or an unbalanced to balanced, probably a 1-to-1 ratio, and the output of that then is fed up to this board, and this uses the good old push-pull configuration audio power amplifier transistors, which then use obviously the push-pull arrangement with the supply voltage to create the audio output to a loudspeaker decoupled through this capacitor. That's normally what happens there. So it's quite a nice little radio. It's, you know, it's all quite easily repairable, and it was designed to be repaired as well. None of this throwaway old rubbish that we've got today. I mean, we bought one of these. These were very expensive, by the way, in the day. When you purchase one of these, you know, this wouldn't be £20–30 radio like you get these Bofang Chinese things today. This would cost you, you know, a few £100. Even back then in the 1970s, you know, it'd probably be the equivalent to somebody's year's wages to purchase one of these. So again, that's a little rundown there. But as you can see, I mean, there's some of the early, I think this is mainly silicon transistors, but prior to this there'd been germanium. There probably are some germanium transistors in this, come to think of it, but there'll be some silicon as well, particularly germanium diodes as well, and things like that used in AM detection on AM radios. But again, you can see the process. We've got the incoming signal from the receiver. We then filter it, amplify it. We filter it again, amplify it again, because every time we filter we may have losses. We mix it. We then get an IF output. The IF output then has to be filtered again. Then it has to be down converted again from 10.7 megs to produce what's called a second IF, because this is the first IF. Then we have a second local oscillator, which is running at a one fixed frequency all the time, which mixes with this signal coming in from 10.7 to reduce it down to 455 kilohertz, which is then filtered again here. It's then amplified and then demodulated, then converted into audio component, which is then fed out on this transformer, and then fed up to the audio power amplifier circuits and squelch, Schmitt trigger, that kind of thing, to mute the audio when there's no RF carrier present. And then we basically have an audio output as well, which then goes off to the loudspeaker. For the transmitter side, a bit more simplified. Obviously, you have obviously audio circuits that clip and prevent the radio from over modulating, because naturally we have to set up the transmitter so that it can cater for the speech band, and at all frequencies it remains uniform and flat. So if you adjust the output at 1 kilohertz mod, for example, to be say plus or minus 2.5 kilohertz deviation for the transmitter, and say you put a 500 hertz tone on, it's now doing 10 kilohertz deviation, and with 3 kilohertz tone it's doing 40 kilohertz deviation, then it's not uniform. So again, there's pre-emphasis and de-emphasis in the microphone circuit, a flattening aspect to it, so de-emphasis, so that it remains uniform across its entire operational frequency range for the audio input, and then that produces a uniformed output, AF output level, which then modulates the crystal itself. And the crystal is modulated with the audio content from the microphone circuit amplifiers, and the modulation is applied to the crystal across that, and then it basically influences the frequency. It will modulate it plus or minus of a carrier to give frequency modulation, and then that would then be multiplied up and amplified, multiplied, amplified, doubled, tripled, whatever, to get to the desired frequency that we want for the transmitter. Final amplifier, which will probably give maybe 400 or 500 milliwatts at this stage at the frequency wanting into here, and then this amplifier then would amplify that few hundred milliwatts up to say maybe 10, 20, 30 watts. We then feed it through another filter which is tunable, and then it arrives then at the aerial socket on the front. So that's just a little rundown of the PYE Westminster, and naturally with it not being synthesized as well, and having hardening concepts to its design and filtering, then it is designed to sort of withstand quite a lot of the effects of EMP. It's obviously effectively in a Faraday cage as well, because of its screening cans are so thick, they're about 3-4 millimeters thick, maybe more. So you know, it is designed for a sort of a nuclear war kind of scenario. It's certainly bomb proof. EMP's protection is given externally using external filtering and suppression to prevent an antenna from coupling EMF from an EMP pulse into the receiver or transmitter and damaging it. And again, the power supplies were always fed through tempest filters and such like, in order to prevent EMP from entering these units as well. So there's a lot of emphasis to protection when these radios were installed in nuclear bunker installations, civil defence bunkers, etc. So that's a little rundown on the PYE Westminster. Right, we've got the transmitter section exposed at the moment, and obviously these radios were built to last. They were built to be maintained and repaired to individual component level, and so they always made adjustments, alignments and repairs easy. So this cover slides off when you've loosened the screws off, and then you can expose the transmitter PA section. So let's have a butcher's. So basically we've got, again, all hand assembled, none of this robotic automatic assembling rubbish that we have today. This was, you know, the height of employment back in the 1970s, 80s, where there were thousands of people working at PYE Telecom and Philips Telecom after that, assembling these individual, winding these manually and soldering them in manually as well, these capacitors, the ceramic caps, etc., and the silver plated wire. And again, all hand done, you know, and all tuned manually as well, you know, using there were assemblers in rows assembling this type of equipment and testing it, etc. So on a production line footing. So again, we've got the RF power transistor there. It might be an MRF237 or an MRF630 or a 2N treble 2, I think it is, the common RF transistors at the time for VHF. Then we've got down there, hidden away, another RF power transistor just here as well. That's another one. And it's quite difficult to see with the design of them, but the earlier RF transistors, some of them had exposed transistor dies on them as well. But these are more like diodes with the way that they mount, with a stud at one end that bolts onto a heatsink, and then you have two conductors sticking out the end. So they're not like some of the RF transistors that we commonly see today with the arrangement that they currently are in, the package formats. These were the early types. And again, we've got a very similar thing. This is more like what they are still today in this kind of format. This is probably made by TRW or Mullard, that transistor there. I'm not sure what part number it has on it, but it's a BLX, so it'll be Philips. So Philips used to make the Motorola, Mullard, Marconi or AEI semiconductors. There used to be quite a lot of manufacturers, Mitsubishi, but back in the 70s there were mainly Mullard, Philips, AEI, a lot of these companies, Motorola, and then of course we've got the harmonic filter there, tuning filter for the get rid of any unwanted harmonics and suppress off before going to the transition to coaxial output as well. And they often needed maintenance, these radios. I mean, they weren't exactly 100% reliable because of the fact that temperature affects crystals adrift. So these were mainly under preventative maintenance. Every year, radio engineer came out to adjust them, align all the crystals. The radio was sent back and a service spare put in, and it went back to a central repair workshop where these were all repaired and maintained all day long in the Home Office. The Home Office Directorate of Telecommunications, or DTELS as it was known as, again another place that I used to work at before it became NTL, National Transcommunications Limited, under privatisation. Used to hold all the contracts for maintaining all the emergency service radio equipment, so these would go back to a central repair facility where I used to work, and they would maintain the radio and repair it and have all the spares, adjust it, the lot. So it was all done there in mass volumes. But at least, again, it was built to last. You know, it would see out 30, 40 years. I mean, considering this was made in 1970s, you know, it's well over 40, 50 years old is this radio. And again, when you look inside, it looks like the day it was made, you know. It's in very good standard, you know. It could work today if I put crystals in, which I might do actually. Put some crystals in and get it going. And you used to pick these up at radio rallies because people used to convert them to amateur radio frequencies. And they were banded, obviously, you know, 68 to 88 megahertz for VHF low band, 136 to 174 for VHF high band, and 403 to 470. These are traditional bands that we have today, but back then the 68 to 88 megahertz were quite common because it was quite a narrow bandwidth, 68 to 88, so the radios could normally accommodate that entire bandwidth. However, 136 to 174 was an issue because they used to do like 136 to 156 something megahertz or 148 megs, 136 to 148 or 150. And they were 150 to like 180 then or something like that. So they had like two bands did in the VHF as well, and then UHF would break it up even more, you know. So it'd be 403 to 433, 433 to 438, and 438 to 470 megahertz. So there were design challenges with a lot of the radios because obviously we're using discrete components, and the way that the radio was designed, with it not having capability to tune electronically, and it was a mechanical tuning mechanism, then sometimes the frequencies could only jump so far. So if you had crystals in and the shift between the frequencies or the splits were too wide, you'd need to realign the radio. It only had a predetermined bandwidth that the radio could transmit and receive in without degradation of the receiver or the transmitter. So for example, if you had a crystalline at say 148 megahertz and on channel 1 for receive, for example, and the next crystal made the radio receive on 168 megahertz, that bandwidth would often mean that you need to adjust the radio. So you had to be careful with choosing what radio frequencies per channel you went in the radio, so that it didn't jump about all over the spectrum, because if it did, and if it jumped about all over VHF spectrum, the front end tuning would need to be redone, and some other tuning as well would need to be done, mainly in the front end section though. And likewise on the transmitter section, the power amplifier would be tuned to say whatever channel 1's frequencies, for example, and then if it jumped too wide, if you put a crystal in that was outside the normal frequency operation band, the multipliers might not tune up, and or if it did, that the transmit PA would need retuning. It might give, instead of 10-15 watts out, it might only give 6, for example. And likewise the multiplier, depending on what temperature things were as well, because a lot of temperature influenced these. You know, it influenced the frequency drift on the crystals. The multiplier stage, if it was cold and it was adjusted right on the edge of its frequency lock, you know, where it could grab a harmonic and amplify it in the double or triple or quadruple section, that if the frequency split was too wide, it would just fall off the alignment, the edges of the alignment, and so sometimes it would work, sometimes it wouldn't. Again, temperature specific, all sorts of different things could occur. So you generally had to be very careful about choosing what radio frequency splits were the difference between the receive frequencies and likewise the transmit on multi-channel systems. So yeah, that's a little rundown of the old PYE Wessie, as they call it, the PYE Westminster. Been around for many years, and still to this day a good quality radio that works. You know, none of this digital rubbish, and nuclear bomb proof physically as well as electrically, and you know, EMP proof to some extent, obviously, you know, with external protection for the antennas, but you know, you get the gist. It's a well built radio designed to last, in this case, 50 years, and you know, it would still be a good working radio today. So that just shows you the quality and the concept that was behind them, to keep things going and not throw away and dispose of things like we do in the modern world. So that is the little rundown of the old PYE, and we'll move on with other things. Okay, just to talk further about choosing, you know, crystals and things like that, and the types that are available. I've got a little selection here of what they'd look like. So this is, for example, the size of crystal that would be going in these sockets that are under here, and naturally the manufacturer's logo is written on the outside of them, and the frequency that's on them. But you'd have to calculate the frequencies. These are 41 megahertz crystals, I think, if we just open them up and just have a look inside. So depending on the multiplier of the radio, of course, so that's a 41.4875 megahertz crystal. So that, depending on what multiplier you use that, if it was a doubler, it would obviously be 82.8 whatever megahertz. If it was a triplet, it'd be so on and so forth. For quadrupler, you know, that kind of thing. So I think you get the idea that you would need to know the multiplication factor of the multipliers, which are used obviously on the in the case of a transmitter, for example. And generally speaking, we have the same with the receiver section as well, which is this side, where we would perhaps double the signal up. The transmitter could be a quadruple stage doubler. You know, in other words, it would quadruple the frequency of the crystal. So they went in, plugged in down here. Now if we look carefully down there as well, you'll also see there's some trimmer capacitors here. And what we did when we used the term netting of a crystal is that when we set up a receiver crystal in there and we align the receiver as per the procedure that I showed earlier, with adjusting this section and then the multiplier stage and the local oscillator, and we get it all rocking and rolling as a radio receiver, the crystals might actually be off frequency just slightly. I mean, the capacitance and all the circuit variables alter the frequency of the crystal slightly, and so these trimmer capacitors we used to net the frequency of the crystal. And how we did that is we had what's called marker oscillators, and I've got some somewhere actually to show you. There were two versions available with rocker switches, and one did 10.7 megahertz and the other did 455, so depending on 21.4, because there were different IFs, you see, for different radios. So in this case 10.7, you would have this little handheld marker oscillator, it was called. It had a little aerial on it, and you would press it was battery operated, you press the button on it and it would generate a 10.7 megahertz radio signal, bang on, and it would beat with it would heterodyne with the 10.7 megahertz coming out of here. Now obviously, if say for example the frequency of this crystal was 1 kilohertz higher or lower than we needed it to be, and we generated a 160.7 megahertz signal in here, and when we were pressing the button on the marker oscillator with a blank carrier with no mod on it, you would hear the difference between the marker oscillator and the local oscillator output, or the IF output here. So if this local oscillator, this crystal and this local oscillator stage was slightly up in frequency or down, you would hear that in audible tone coming out of the radio speaker, and so it would sound more like a whine, you know, sort of sound, you know, depending on how far a frequency it had gone. And so what you did is you then tune this capacitor that was adjacent to the crystal you were netting against this beat where you were pressing this button on the marker oscillator, and you would reduce the signal, the beat frequency, right down so that basically it was like a so that sort of sound, a flutter of the lowest order you could possibly get, so that was bang on. So it meant that the marker oscillator and the receiver were on the same frequency, and that meant that the crystal was netted. It meant that then the received crystal was on the correct frequency that it should be. If it wasn't on the correct frequency it should be, it means that the local oscillator would essentially desensitize the receiver, because the mixing between the desired signal that's coming in here and there will be too far off for the receiver to adequately receive, and therefore it would affect the sensitivity of the receiver and its performance. It would be distorted, it would have all these undesirable characteristics. So that's why we needed to make sure local oscillator frequency was spot on, and we did that by netting the receiver crystals. So that's how you did it. You ordered the right frequency crystals, taking into account of course that after you'd done the multiplier, the local oscillator had to be higher, what we called high side injection, or low side, exactly 10.7 megahertz lower or higher than the input frequency, and therefore the output would be 10.7 megahertz, which will be received by this. This can only deal with 10.7 megahertz, you see. It can't deal with any other frequency. So all the undesirable components that are coming in the radio spectrum, all the other adjacent channels and other radio traffic that's on the radio frequency spectrum coming in here, because everything comes in there basically. It's the selectivity. We're selecting a desired radio frequency that's coming in, and we do that by mixing it with another signal that's locally generated to produce an IF. Make no mistake about it, on this section here there's also a load of, even though it's lower at 10.7 megahertz, it's a mirror image of what's coming in here, but just at a lower frequency. We've shifted a very high frequency down in frequency to a very low, but yet there's still lots of other signals present near the 10.7 megahertz, which is a mirror of what's coming in from the antenna, and we need to get rid of those, and that's why we use a 10.7 megahertz filter. So any adjacent channels or radio signals that are still in that frequency band that are undesirable are got rid of by this filter, and only the desired frequency we want at 10.7 megahertz, the difference between these two, is allowed through this filter, amplified. And then again we have a fixed local oscillator that just runs at obviously the difference between 10.7 and 455 kilohertz, so that produces 455 kilohertz IF. So this oscillator running here at fixed frequency mixes with the 10.7 that's coming in through the filter in a mixer here, and the output component is 455 kilohertz. So it's if you like, it's a double conversion. We've got a first IF and a second IF, and then again all the unwanted components that are coming into this side of the filter got rid of. The filters all have losses, so naturally they all have amplifiers as well after them to follow them, and then we get the signal that we want at 455 kilohertz, and then we have to demodulate it. Now on the crystal footing, we've got all kinds of different crystals, and of course these are still used today, crystals in modern computing, as well as time clocks, things like that, all kinds of different frequency standard applications. We have oven we have oven jackets that the crystals go in to keep them warm as well, because some crystals need to be temperature controlled in a crystal oven so that their accuracy is maintained for very high stability applications. So as you can see, they come in all kinds of different sizes, widths, lengths. They all have different applications. And then of course we've got the likes of the crystal filters as well. These are all obviously the very same kind of construction as what we've got there with the ITT one, and they in turn as well come in variable sizes. So some are even bigger, some are enormous. I've got some that are bigger than your hand, and we've got all kinds of different filters. What's this one then? Frequency cal. It's giving you temperatures. So there are crystals that are used as reference oscillators to produce reference signals for systems and clocks, and for synthesized radios use reference oscillators as well. So that's an older version of one of those. And then of course we've got IF filters. So crystals are used in all kinds of different applications, not just for generating frequencies but also for filtering as well. So this is again another example of a crystal filter, and again, we've got a lot of these companies have gone out of business now, but we used to make all sorts of things in the UK in the bygone days, and that'll tell you, I think that says it's 100 kilohertz, I think, if I'm not mistaken. Yeah, bandwidth for 100 kilohertz, 1.4 megahertz center frequency, or 1 to 4, probably 1.4, but that gives you the idea of a crystal filter. Again, very similar application to what we looked at before on the radio. So there's all sorts of little bits and bobs, you'd be surprised. And we've got some fixed frequency crystals here. I think these were made by Marconi or somebody, and these are 10 megahertz bang on, these crystals. So these are all wrapped up, and they were easily damaged as well, crystals. If you drop them on a hard surface quite hard, you could damage them quite easily, so that were another thing that you had to be careful of. So these crystals, I keep them because I have all sorts of requirements for crystals in design work, but there's all sorts of different there used to be all sorts of different companies, but I don't know who makes them anymore. I haven't kept up to date with it, but I don't think there'll be many companies in the UK now or around the world that make them. But again, another bit of a bygone era. I managed to find in the collection a crystal that's transparent, so we can have a good look at it. So that's basically the crystal element, and as you can see there's like a wafer and then 2 electrodes attached to it. That's a better shot, I think. There, look. So the left and right, you've got the 2 electrodes which go to the legs, and then in there then you've got the crystal wafer that you can see is the disc, and then on one side you've like a silver tape, and then on the other side you've got a silver tape. So that's how the crystal works, with the disc, quartz disc in between. It's obviously quite intricate to manufacture. So that's a little rundown of a quartz crystal. But yeah, all interesting stuff. And of course, crystals are EMP proof, so great in applications in you know, resistance to electromagnetic pulse. Particularly good in applications for what these radios were used in civil defence. So with regard to modulation, for example, the crystal, the transmit crystal, this is a transmit side now on this section. You would obviously get the right frequency crystal versus the multipliers here to get the right frequency output, fundamental. But down here, the way that they modulated the FM onto these, in some designs, they had a transistor junction or a diode across the crystal, and so that they could introduce modulation audio onto that particular component, and it would then influence the frequency of oscillation of the change it slightly of a crystal. And so what would happen is that it would effectively modulate the crystal itself. So when you spoke into the microphone, the frequency of the crystal would be modulated by the audio. Other ways of doing it as well was a very similar thing to the multiplier. So often on the first multiplier there would be an audio input, and then again there would either be a transistor junction or a diode that could modulate the content of the FM onto the carrier, and then it would obviously frequency modulate the carrier in the same way that it would do if you modulated the crystal. So you will see that one side of the crystal goes to a wire, which then goes to a channel socket via the wiring loom, and basically it grounds just one side of the crystal to select the channel. So that's how you can have 10 channels. They just have 10 wires coming off for each of the channel, and that then is taken through a selector switch to ground, so then each channel can be selected appropriately. To align the transmitter frequency onto the correct carrier frequency, again similar to the receiver, you use these variable capacitors. So you would adjust these variable capacitors to get the right frequency of a transmitter on a frequency counter, for example, so that the frequency the transmitter was on. Otherwise, if it was too far off, it would not be receivable at the other end. So that's a little rundown on crystals, alignment procedures, things like that of this radio. Okay, this little radio transceiver, this PYE Westminster one, there are 2 models in the range. There was a small compact one, which is this, which went fitted to motorcycles, and under dash in vehicles there's a bracket that goes round it that allows you to fasten it to the underside of a dashboard in a vehicle, and then the mic just plugged in there. And then they did the remote mount version of the PYE Westminster as well, which was great for things like fixed installation at hilltop radio sites, where you could have a line output, or via a PSTN phone line, or you could have it in a equipment room in a building or a bunker, for example. Then you had a remote little control unit, which is about that size, that connected to this on an umbilical cord, and then you could control it from a desk or something like that. Or they could be mounted in a boot in a vehicle, and then you could have a control head up on the dash at the front. You chose that depending on what type of installation you wanted, whereas this was quite used extensively in the 1960s and 70s on motorcycles, particularly police motorbikes as well. Obviously it's got an antenna socket on the side, an SO239, and then you have on the front the channel switch, which selects the radio channel, volume and a squelch control, and obviously an on and off, and a transmit receive light. Now they're very similar internally, which you'll see if we whip the lid off and have a look inside. You'll see that there's quite a lot of similarities between them. Very similar boards and things are used within both of them. There are some slight differences, obviously, because of the size differences, but you know, generally speaking, they're more or less the same internals, the same theory. We've obviously got a row of what would be transmit receive crystals, multiplier stages, etc., which is what these are. Now these transceivers, before we go and discuss the internal workings, had a frequency range, according to the technical blurb I've got up on the computer, 25 megahertz to 174 megahertz in 9 bands. So that's why I said in the early part when we were looking at this, how they're available in all sorts of different frequency bands. So from 25 megs to 174 they were available in as mainly VHF. They had a channel spacing of 12.5 kilohertz at 20, 25 and 30 kilohertz, or 40, 50 and 60 kilohertz channeling. And they transmitted at roughly 15 watts, 10 to 15 watts RF output power as well. So that's what they had. They had a maximum of 10 channels as well, 10 for receive and 10 for transmit. 12 to 15 watts output power, radio frequency output power, and the spurious emissions was less than 0.2 microwatts at antenna socket, and harmonic content was better than 2.5 microwatt at antenna socket as well. So the modulation was adjustable to 15 kilohertz peak deviation as well. So this was a type W 15, I think it was, FM, that was it's called, because it was a frequency modulated radio. PYE made AM as well, AM radios as well as FM. Quite a lot of the early radios obviously were AM because that came before FM, so they had a big modulation transformer inside. But these were FM sets, so these would have been quite expensive back in the day when they first came out. Now internally within the unit, similar to the previous unit, we've got the what is the transmit exciter multiplier stage here. So we obviously get the RF output going into the transmitter power amplifier block, which is this section here, and this then obviously amplifies up to 12 to 15 watts. We've got an antenna filter section here, and then that's coupled out to what is this RF relay. This is an antenna relay, changeover relay, so the aerial socket's here, the antenna socket's connected to this relay, and this relay then being a metal canned enclosure isolated relay, switches between the transmit and receive paths. And then obviously on this section here, this is the receive mixer stage. So we've got basically the receive front end is connected to the antenna via the antenna switch, it's amplified, and then with a mixer stage here. Now we've actually got you might not be able to see it clearly at this stage, but we've actually got some coaxial inputs here from underneath, and there's another board on the other side which I'm going to show you in a moment, which gives the injection there for the local oscillator for obviously producing what's called the first IF, the first intermediate frequency. So we'd peak these coils here for maximum receiver sensitivity on the VHF frequency we're wanting to receive from the antenna. The amplifiers, transistor amplifiers that you can see, there's one there and one there, will amplify the RF signal up as it passes through these helical resonators, and then we'll pass that filtered signal then into a mixer stage, which is down there. That's the mixer section down there, and we've actually got a mixer transistor there, diode, which will mix the local oscillator signal with the incoming RF to produce the first IF. Now the first IF will run at either 21.4 or 10.7 megahertz, which will be filtered by this crystal filter, and then it'll be amplified up, and it'll be mixed then with a second local oscillator frequency, which is from this crystal here. So this is fixed because the input from this is fixed at either 10.7 or 21.4, whichever this filter is designed for. It'll mix with this. So those two are fixed, if you like. They're non-variable in the frequency. So therefore all the pre-selection is done prior in this section. So the local oscillator input there moves frequency as you change the channel switch. Obviously, and the crystals are selected, the local oscillator frequency moves to mix with the incoming signal to produce what is a 10.7 or a 21.4 megahertz difference between what you're receiving from the antenna and obviously what's being injected there to produce the first IF. And that first IF then mixed again here with the input from this crystal local oscillator, which is running at a fixed frequency, and that then produces a second IF. So it's a double conversion superheterodyne receiver, where it then converts it to a second IF, which will probably be 455 kilohertz intermediate frequency, and that then is passed to this board here, which is the discriminator section and audio power amplifier. So this has the pre-emphasis and de-emphasis, the squelch circuit, and the discriminator, which receives the FM content from the carrier wave and strips it off from the carrier wave at 455 kilohertz. And then these are push-pull amplifiers, which then go into the capacitor on the output as a DC block, and then into an audio transformer, a one-to-one audio transformer. We've also got a nice little relay down here as well for switching probably the power supply for the audio amplifier on and off at the same time as going to transmit, so that the audio amplifier in this stage isn't running while ever the transmitter's in action, so we're not getting white noise being fed out to the speaker while we're transmitting. This module down here, let's have a look at that. I think that's a not sure what that is at this stage actually. Let's just have a look, see what I can work out what it is. It's some kind of a filter of some description. That might be a some kind of filter. I'm not sure what that is, to be honest with you, at this stage, but I'll find out what it is. But yeah, the that's that side of it. So we've got the transmit power amplifier section here, and then obviously the transmit and receive relay here, RF relay, and then the TX exciter, which is obviously the TX drive, which produces a signal there. Now I think I can remove these screws. Let's just see if I can have a look at what is the transmit PA power amplifier section, because underneath it there'll be the transistors and the tuning capacitors, which obviously tune up the radio frequency power amplifier stage, so it can produce its 12 to 15 watts RF output power. I mean, you've got to bear in mind, back then, back in the 1960s, 70s, when these radios were manufactured, you know, 12 to 15 watts was quite reasonable output power. I mean, obviously in today's radio standard, it's, you know, it's quite low, considering many radios were turning in the 1990s to Mitsubishi power amplifier bricks that were hybrid amps all in one. So you could do away with all this tuning and big circuit boards with inductive and capacitive tuning, lumped circuits, and multi-stage amplifiers. You just had one little module. So here we've got obviously further tuning coming in down here. We've got the signal and ground path from the multiplier exciter output, which is connected in here. Input impedance matching to the first stage transistor and an RFC to the collector. This will be a bipolar, probably a 2N treble 2, whatever it is, VHF transistor. Silver plated wire. Again, all handmade, all hand wound and hand soldered. No machine assembly back in those days. And that's matched then to the second stage, to then amplify it from a small signal to a power amplifier signal. Notice we've got a centre tap here on this part of the emitter on the transistor, and that'll be manually done as well, you know, to find the optimum RF gain. Again, matching into the next stage, which is this transistor down here. Now I'm not sure, I bet that'll be a Philips. Yeah, it's a BLY whatever it is, BLY 80 something 3, is it, or something like that. So it's a Philips Mullard transistor. That's your final amplifier, obviously, the final stage of the amplification before it reaches the transmit harmonic filter. So again, you know, tune for maximum smoke, get as much RF power as you can out of these with minimum harmonic interference, and that's basically that. But on the other side, of course, on the other side, this is where we've got a bit more going off insofar as what would be the receiver and transmitter side of things. Now they do use for microphone matching modulation transformers, or microphone 1-to-1 or 600 ohm to high impedance or low impedance transformers. But again, we've got the crystals for both transmit and receive. We've then got a microphone amplifier stage as well, and there's a switch here, look, off on. I don't know what that is, probably for something, maybe some test mode or something like that. So looking in this section, just trying to get my bearings as to what's what. This looks like as if it's probably the microphone amplifier. This stage takes the mic input from the front, and that's your deviation adjustment or your mic gain, and that then produces the transmitter FM modulation. These are the crystals again. This is some kind of multiplier stage for either the transmitter or the receiver, likewise with this one as well. This looks like it's some kind of squelch circuit. I think that's part of this volume and squelch thing, some kind of audio processing stage with the look of it. So let's see what we can see. Yeah, oh, that's the IF section there, look, 455 kilohertz. So that's the IF intermediate frequency. So the second IF that comes from mixing on the other side, which is this bit here, this signal here is coupled back underneath to this board then for demodulation, FM discrimination, and then that's then passed back up again to the other side to the remainder of this PCB and this one then for the squelch, hysteresis, and obviously the power amplifier push-pull stages for the speaker output. So that's basically the receive section. This will be the transmit multiplier stage, I believe. It might tell us actually on the boards. It might do. Let's have a look, see if it says anything. But I'm sort of 100% certain that that's what that is. It's a TX multiplier or something of that stage. Again, that's part of it. So you got your multipliers, and then obviously all your audio stages, etc. So that's a little rundown of that. And what does that say there? Facility. Yes, we can add a facility on it. So yeah, quite an interesting little radio. No crystals in it though. Might have to put some in and tune it up, see whether we can get anything out of it. But yeah, very well made, aren't they? You know, they're not rubbish radios. They're very, very well put together, and obviously the workmanship that's gone into producing them is second to none. You know, don't get that kind of workmanship today. So that's a little rundown of the little PYE Westminster then. So at least you've seen what's in that. Now these are great little radios for learning RF engineering and design of radio transceivers, because the modular design allows them, if you get one of these from an auction or a sale, whatever, you can remove the boards and you can then make your own radio receiver, basically, essentially, because they're quite basic how they're wired and put together, and it's quite easy to reverse engineer, and the service manuals for these are still readily available. So you can sort of remove the RF front end section if you want, and you could feed in a signal generator, you know, in here, in this coaxial input there for the mixer. This is your local oscillator input. You could feed that to an RF signal generator or synthesized signal generator, and then you could then choose which RF signal you're receiving in. Obviously, if you used it in synergy with this board as well, which then gives you the 455 kilohertz along with this one, you could effectively have a VHF receiver just in these three boards, because obviously you're mixing the incoming RF signal with an input from your signal generator, plus as well this is the IF down converter, and then obviously mixed with the second local oscillator. And then if you remove this board as well, which is obviously the receiver 455 kilohertz discriminator, you're going to get an audio output off of that. So you can break it down into modular components or modular areas, you know. You could even put a 455 kilohertz receiver on the end of that, a scanner receiver or a ham radio receiver that's capable of receiving 455 kilohertz or 10.7 or 21.4 megahertz. And you can mess about making your own amplifiers and learning how sensitivities of receivers are adjusted, and you could add extra amplification if you wanted to, or remove it, and you could experiment. You could do all kinds of things, you know. There's quite useful components and parts in here. You could even leave it in situ as it is now, and then just feed a local oscillator signal there in. So you could basically use an RF signal generator to change the frequency of your radio receiver, and then you could turn this into a receiver that's quite a wideband VHF receiver if you wanted to. You could do all that just by using these existing modules that's within the unit. So, but what I'm getting at as well is the fact that it's got the building blocks of a radio, obviously, which are quite clearly set out. So to get somebody who's trying to get into RF and understand it, this is quite a good example of this radio, because you can obviously pull these you know, these cans off and have a look inside at the things. You can change the windings on these, and obviously decrease its frequency so that you can get it onto other bands. You can convert it, you can increase the frequency as well by removing turns and manipulating the tuning on these so that you can get them to go into other frequencies. Experiment by putting different variable caps in and twiddling and tuning, and you can play around, you know, and you can get to know, then you get the feel for RF applications in receivers, and building your own receiver and getting confident in being able to design your own radio at some stage in the future, or even manipulate an existing radio to get it onto frequencies which it wasn't designed for example. So you can do all that with these old radios, and as I say, most of them only need a supply, and they've got an AF output for an AF stage, or they've you know, an RF in and an RF out. As you can clearly see here, you've got the coaxial feeds in, so it's really interesting stuff. You know, you can get right into it. Everything's so accessible. You know, you can pull the cans off as we've just done. You can play around till you're blue in the face with it, and you can design your own little radios and everything with it, and you can get that fundamental knowledge of experimentation. It's all very well reading books and getting yourself familiar with theory and mathematics, which goes in deep level into RF electronics engineering. But at the end of the day, you can't be hands-on. You know, having a play yourself, and you learn so much through tuning things and getting to know how a radio works and what doesn't work. You know, some ideas, and you can obviously, you know, you could remove that device down there, for example, and put a gas FET amplifier in on a little retrofit board and improve its noise figure and its RF gain tenfold, you know. And as I say, you can feed in a local oscillator signal there from an RF signal generator that you've got on the bench, or you know, these days with software defined radio, you can get them to generate an output which you can feed in there, and you can control the radio and turn it into a proper radio receiver. And so you could do it with the transmitter side as well. So there's lots of learning material in these radios and development skills that you can acquire by delving into the individual circuit boards and how they operate and what they do. And combined with the serviceman and the schematic diagrams as well, it also gives you that added benefit. I mean, these days, in today's society, obviously we have an entire radio on a little chip, you know, but it doesn't teach you the fundamentals and the basics of RF engineering, and that's what this kind of equipment does. It gives you an insight into you know, the dark art of RF, and you can experiment and play around and produce your own designs using this type of equipment as well. So there's quite a lot of useful parts, quite a lot of very easy to play around with componentry that you can really get hands-on with, doesn't need a microscope to work on, because it's surface mount. It's clearly you know, designed so that you can work on it. So, you know, it's a real benefit to anybody who's wanting to get into RF engineering, even at a basic level, just to get the fundamentals under your fingertips. Well, I said I'd find out what that little module is, and I don't know why I didn't work it out to start with, but when you're doing a video and trying to talk at the same time, sometimes you lose track. That's a 455 kHz second IF filter. So obviously we've got the first IF, basically the first mixers here. RF comes in, mixes with the first mixer, local oscillator signal to produce the first IF, and then the first IF mixed here again with the local oscillator crystal, which runs on this board, mixes with that to produce the second IF at 455 kHz. That goes through to the other side, which, as we saw, this board here, which is labelled up the 455 kHz discriminator board. So this is where the FM demodulation takes place, and the signal from this at 455 kHz is fed off underneath, down here, to this filter, 455 kHz. So basically the output of that then being filtered is passed back to this board and then processed for audio, and ultimately this board amplifies it to pass it through a DC blocking capacitor to a loudspeaker. So again, you know, simple terms, simple things, and by removing these modules, by taking these out, and you can put spectrum analyzers on different places using SDR, software defined radio as well. You know, you can do so much with it. You can manipulate RF going in as well into these filters and see what's coming out, and likewise you can remove the filters from circuit if you want, and then see what the effect of that would be by removing these IF filters, and what influence that would have on the degradation of the receiver or its performance. And you can get to know so much then about mixers and the image frequencies, and the aspects surrounding interference, you know, from if you didn't have those filters in, obviously you'd receive quite a lot of interference from other neighbouring transmitters near the frequency that you're wanting to receive. So it will give you an insight as to how important these filters are and what role they play within the unit. And you could even put your own filters in as well at different bandwidths, narrow and wide bandwidths, and change its characteristics and make it receive wideband FM, and put it on the broadcast radio bands, for example, so you could listen to FM radio on it. You could do all sorts of things, you know. It's quite interesting. So yeah, that's that little rundown, and I hope you've enjoyed that. So by now you'll have understood that this item is a nuclear radiation dosimeter, which we'll have a look at quite carefully in its calibration, charging and operation. And these two devices here are the chargers that charge up the dosimeter. And the unit of measure that these employ is the Rentgen, or Rentgen, depending on how you pronounce it, whether American or British. But basically the scale in this, which I shall show down the little spy hole there, reads Rentgen in a level from 0 to, I think it's about 150, something like that. Let's just have a look, see if I can see down the hole, if I can get it to work that way. Let's have a look. There you are, look, it's it's just there, look, Rentgens, and I've calibrated it already, the marker to the 0 there. You can see the line, which is what you do with the charger, which I'll show you. It goes right up to 150 rads basically. So that's the level of radiation that this dosimeter can measure. Now that unit of measure, Rentgens, is not used anymore really, insofar as calculating, or what I mean to say is that the way that these meters work is that it's ionizations in the air. So as radioactive rays hit this dosimeter, it then displaces, or basically the charge within this unit, and then the needle will move, or the marker will move, to display the unit of radioactive measure. Now there's a calculation which you have to do, because really the difference between the level of Rentgen and the tissue damage that it can cause to a human being with ionizing radiation, there's a calculation that has to be done in order to do that, which I'll go into a bit later. But basically, back in the Cold War days when this was about, there was a certain level of radiation that if you were exposed to it within a certain period after the atomic bomb had gone off, basically, depending on what dose you got, would then calculate whether it was a fatal dose, a non-fatal dose, and then it would also calculate, using that information from when the weapon went off and when you receive a dose, might also give an indication as to when you may die, simply because of the fact that radiation sickness is directly proportional with a fatal dose in the time in which the weapon went off versus when you receive a dose, versus how long you've got left before you'll die of radiation sickness or radiation poisoning. So that was pretty useful for civil defence in looking at the dose. Obviously this is a non-reactive dosimeter, where once you receive a dose you won't know until you look down the little hole there. Obviously modern dosimeters now measure sieverts, millisieverts, and you can directly calculate easily the tissue damage caused by ionizing nuclear radiation to the human body. Whereas with rentgens it's a little bit more difficult because of what different tissues absorb things differently, or can be damaged differently depending on what the dose is. But back in the days, in the 1960s, 70s, 80s, when these were about, before the digital versions came in, you know, there was no warning as to what dose you'd receive till you looked down that little hole. So really it was very dangerous, you know, times. And not only that, in the height of the Cold War, when these were regularly given out to military personnel and civil defence workers and public service workers and things like that, there wasn't really an alarm like you get now on current dosimeters, where you expose yourself to a certain level of radiation or whatever and it'll trigger an alarm so that you can remove yourself from that exposure as quickly as possible. And of course with nuclear radiation, ionising radiation, it's all about exposure time, and this device doesn't tell you how long you're being exposed to a particular source of radiation. It only tells you what level of radiation that you're being exposed to, which is no good after the event really, is it? So, you know, they were handy for certain uses but not so good in others. But then of course these were invented long before digital technology came about. So these chargers charge the high voltage electricity into the dosimeter. They plug in the bottom, and basically there's a socket here which is under this cap, and basically the dosimeter has a little plug at the bottom here which comes off, and a connector, electrical connector, and then you basically sit it on there, push down, and then it starts to charge it, which I've done. And then you use this this potentiometer here to get the line that we saw down there onto the 0 mark. So you calibrate it for 0, and then basically then you're good to go. And obviously then once you expose it to radiation, that needle will move up and down the scale, you know, but as we saw, it was down here at the 0 mark. So obviously as you expose it to more radiation, the line will go up to whatever radioactive level has been recorded. So that's a little rundown of that, which obviously insofar as the electromagnetic spectrum is concerned, you know, you've obviously got radio waves, microwaves, then you've got ultraviolet, visible light, etc. What is the visible light spectrum of red, green, blue, etc. that we see through our eyes. And then higher than that, then you've got X-rays, you've obviously got alpha, gamma, beta, etc. rays, which is the ionising radiation area, and cosmic rays, etc. So this operates at the very high end of the electromagnetic spectrum, if you like, or the ionising radiation spectrum. So we move from the electromagnetic spectrum into the ionising radiation. So as far as this is concerned, this uses displacement of electrons, obviously the charge that's built up in here by the charger, to then read radiation levels. So I'll go into in a moment the differences between what this type of meter can do versus the newer types. I've got all sorts of different ones of these. I've even got the modern digital ones that go on your wrist as a watch, and other types of radiation meters which I'll be showing. But again, this is old Cold War technology from the 1970s, 80s, and the 60s, 70s, 80s sort of thing. So these were issued to NATO and forces around the NATO military countries. So that's what they used. But they are hand cranked. This one's battery operated. It takes a big D-cell battery underneath, which we'll have a look inside there. And this one's hand cranked. So, you know, we've got a switch down here to charge the device or to discharge it by pushing that up. And then we've got like a bit like a windy handle, like a dynamite blasting thing to charge it up. And then we've got a hole down there that the dosimeter plugs into when you're doing your charging, etc. So obviously you can't rely on, you know, very heavy, but you can't rely on external electricity and things, you know, batteries and stuff. So that's why that's hand cranked. So we'll have a look further into the units of measure of ionising radiation and how we can calculate dosage to a human being, which interestingly has changed throughout the years, you know, back in the 1960s, 70s and 80s, in the Cold War, when we were looking at what level of exposure would be fatal for somebody if they were exposed to radioactive fallout from a nuclear explosion. Then that figure sort of changed over the years, and the damage and things that can affect a human being. And there's certainly been a lot more information come out and research and development over the years, particularly after the Chernobyl incident, and now there's a lot more understanding of the effects of nuclear radiation on the human being and on tissues and DNA and things like that. So I shall come back in a sec with a bit more information on that. So before we break all this apart, I just wanted to talk about what's called the SI units now, which is what we commonly use in modern dosimeter technology that's available. And there are two things really. There's the grey, which is about energy absorption. So that's the way you start really with dosimetry, which is it's the stopping power. You know, it's the exponential attenuation of a neutron reaction rates and things like that. What's known as scattering absorption, and you calculate energy disposition in tissues and things like that. And basically there's a formula for it, which is basically 1 grey, which is GY, in brackets equals 1 over the kilogram in weight of the tissue which is absorbing the radiation, because obviously there's a connection between the biological and radioactive element, which would then obviously damage the tissue or the DNA, and then obviously cause death or severe sickness, radiation sickness, through receiving a dose. So these days we talk about sieverts, which is spelled SIEVERT or SV in brackets, and basically depending on the tissue types, we use what's called a Q factor to convert GY or grey into sieverts, and this is what most modern digital dosimeters use today, is measurements in sieverts, because with sieverts you can directly calculate, or it can be done quite easily on a graph or whatever, the differences between the biological effects and chemical effects in the human body versus ionizing radiation from radioactive fallout, for example, from a nuclear weapon. And so therefore it's easier to calculate damage to human DNA and tissues from a radioactive substance than it would be from a rentgen. So this is why these meters were quite old-fashioned in the terms of calculating a fatal dose or a non-fatal dose of somebody who was exposed. And that's also another reason why civil defence people who had these and army personnel were taught that they had to take readings on this every 5 minutes and then log what the reading was. So therefore they could calculate the exposure time and the level of exposure, which would then equal whether they'd received a very nasty dose, a slight dose, or a fatal dose. And from that information of time versus exposure, or exposure versus radiation level, then you could calculate whether that person had received a very dangerous dose, a fatal dose, etc. It's all serious stuff, really. So this is why SI units are mainly used now in modern measurement techniques, because of the accuracy that it can give towards the chemical and biological disposition in the human body. So yeah, so there's various formulas for it, but that's how you can work out, you know, the differences. And often these dosimeters will have information with them that will show the unit of exposure over time equals what level of types of damage to the human body, and there's quite a lot of information out there about that already. So one of the other conversion or units is basically CGS units as well. Now CGS is basically, there are two types to this. There's, for example, 1 rad equals 100, and then 1 gray basically equals 100 rad. So you've got rentgens equivalent, you've got 1 sievert equals 100 rentgens. So that's basically what are the CGS units. So again, this is where we're looking at, it's defined basically when you've got 1 rad equals 100 ERG, absorbed energy per gram basically. So ERG is energy per gram. So it talks about more, instead of kilogram, because if you remember earlier, 1 gray equals 1 over the kilogram basically is 1 gray. We're talking about units of radiation measuring kilograms of whatever tissue or absorbing material that the radioactive substance or radioactive rays are colliding with, whereas 1 gray equals 100 rads, and likewise 1 sievert equals 100 rentgens. So we're just talking about the different types of radiation as well. There's obviously alpha, gamma, beta, and so gamma radiation, it's quite convenient to use grays, for example, where with alpha, beta and other types of radiation, there's these Q factors or quality factors, and then you can convert them from grey to basically sieverts. So it's quite a complicated thing really, and this is why it's so often the case that you need these conversion charts when you have these, so that basically in the case that these were used in anyway, as far as radioactive fallout were concerned, obviously, you know, you've got the main source of radioactive fallout is gamma rays, so therefore gamma, alpha and beta particles can all penetrate different depths in different materials. So gamma rays can go through like 6 foot of concrete, reinforced concrete, for example, and gamma and alpha and beta all have different absorption factors into different types of material, including human beings. So therefore, you know, you have these different units of measure. You have ionization, energy absorption, increased risk. You've also got SI units, CGS units, you've got rentgen, grey and sieverts. So they all have relationships and conversion factors, but the main element is the Q factor, and the quality factor multiplied by whatever the tissue density is would then equal the damage that then can result from that, depending, you know, on the biological chemical reaction within the body. So this is why these were quite a blunt instrument really when it came to, you know, surviving such a radioactive exposure. And so that's why they had charts with these that basically said quite bluntly, if you got this level of exposure, you'll have moderate or mild radiation sickness. If you got that level of exposure, you've only got 2 weeks to live. If you got this level of exposure, you'll die within 24 hours. And if you got this level of exposure, you'll be dead in an hour, that kind of thing. So this is basically why they did these charts. And it's quite interesting really when you look at just how important these were for survivability after a nuclear attack. Because if nuclear war wouldn't be bad enough, you then had to endure the awful aftermath of trying to keep away from radioactive fallout, which, you know, is a product of a weapon. If it's ground burst, it sucks up all the debris and everything from the explosion into the mushroom cloud. The mushroom cloud obviously is radioactive with all the radioactive substances from the weapon itself when it detonated, and the radioactive fallout, which is in the mushroom cloud, falls back to Earth, which is normally downwind from when the explosion occurred. And so therefore this is why, you know, it was so important, particularly with the UKWMO, which is an organisation in the UK that had meteorological, scientific and specialist advisors that plotted radioactive fallout, where the weapon had exploded, where it had gone off, and also the zone of, not just the zone of destruction and the yield of a weapon and what damage it had caused to a city or to a military target, but also the path of radioactive fallout downwind and where that would ultimately settle. And obviously, as far as civil defence were concerned, you were told to keep in your fallout shelter for about 2 weeks with food and water until the radiation had decayed sufficiently enough where it was safe or moderately safe for people to come out of their radioactive fallout shelters to protect them from radiation, and therefore come back out into the environment again. But the reality is completely different to what many people thought at the time. Right, well, we've got the dosimeter charger apart, which takes a D-sized battery, and what they've done in this, it's quite clever actually how they've thought about this. First of all, get some more light on it. You can actually see inside that it's run from a D-cell battery, which is quite good. But we've also got what appears to be a spare bulb as well, and some people might be thinking, well, why do we need a bulb? Well, we've got a spare bulb here, and then here we've actually got a bulb, and built into this socket where the dosimeter plugs in, obviously, is a bit of transparent plastic which goes through onto the other side, which is just this section here. And as you can see, it's got like a transparent lens that goes through with the electrical contact in the middle plus the outer ring. Now what happens is when you put the dosimeter onto this and it pushes down, it's spring loaded is the socket, so as the dosimeter is attached, there's a cap underneath the dosimeter that then exposes the electrical contact, you see, on the inner and outer, and that then in turn mates with this socket, and then it pushes down. It's like a switch, and in pushing it down on the spring loaded contact that's down here, it makes a contact which then energizes the high voltage multivibrator, which is potted. It's here. There's a transistor multivibrator arrangement with a transformer, step-up transformer, which obviously steps up the voltage to many thousands of volts, and it's switched at quite a high frequency to produce a high voltage which arrives here. And of course we've got two wires which form the switch, and then an earth plus a live. So basically there's two parts to this. There's a switch that turns the light bulb on when we push in the dosimeter, so that the light bulb shines through the lens in the socket. That in turn shines out of here and into the end of a dosimeter, and then in the dosimeter then obviously you can use the potentiometer, which is here. This moves, and you can then calibrate it, just the voltage obviously, or discharge rate, through the dosimeter. The electron charge in there is changed by, when you set this potentiometer, it alters the voltage, which is this pot here, and basically then the line which we saw in the, which you'll see as part of this video on the dose scale for rads, is calibrated to 0 position. And so you use that control, you turn that, so that line, it moves about quite quickly actually, but you bring it to 0, and then once you've set it at 0, then it's good to go. And then obviously you can issue it out to people to use then to measure dosage of radiation. So it's fairly simple, it's not, you know, overcomplicated. It's, you know, it's sort of belt and braces. least I thought about putting a spare bulb in, because obviously that's very critical, because without the bulb or a source of light through there to see what where the needle's gone, if you like, on the display, you can't then set the potentiometer to obviously calibrate it. So that's the most important thing of the whole device, really, is having the light bulb. So it's quite interesting, really. There's not much to see really in these, because obviously it's potted. There's a lot of potting going on down there, but basically top and bottom of it is you've got the you know, the potted multi-vibrator circuit and transformer down there, and a high voltage cap, and then obviously the connections going up to the what is the socket for the dosimeter to plug into. So that's that, really. We've got some NATO, I think, part information on there, dosimeter charging unit, and serial number. So that's that. It's quite a heavy, you know, die-cast box, obviously built nuclear bomb-proof. And likewise on this thing, I'm having trouble getting this hand cranking knob off. Rather than having a battery operated thing, again, very similar, except this particular type of charger unit was for a different type of dosimeter than the one that I'm showing in this video. But basically a similar thing, that plugs in, and then you hand crank this handle, which collapses in. You hand crank that. It's a bit like a blasting cap explosive detonator type thing. But here you've got charge and discharge switch, which is quite difficult to turn. Actually, it's quite powerful. So you can charge and discharge it, and what have you. So we'll see whether we can get into this to have a look. But I've had some difficulty trying to get this knob off. It won't shift, so I might have to use brute force to get it to come off, because there isn't a grub screw in there or anything that sort of clamps that to the shaft. I think it's just pushed on, so I don't know how to get that off yet. We'll have to look at that and see whether we can get into it, because if I can't get that off, I can't get the bottom plate out. So on this dosimeter, I forgot to I didn't realise, but there's actually a circuit diagram. Not that it matters, because everything's potted in there, but there's actually a circuit diagram on that dosimeter charger. So this is what it looks like, which is obviously looks like it's using a germanium transistor, I think, being an OC83. So it shows a 1.5 volt battery, the switch, which I talked about on the socket when you push the dosimeter in, and then obviously it's got an oscillator circuit as well, some by these two coils, a feedback coil here obviously on the base, and then obviously on the collector circuit when that conducts, obviously, because it's a PNP transistor. This is taken to ground, obviously, so this starts to conduct, and in doing so it pulls this voltage down through the coil, which then generates obviously an EMF spike, which is on this coil, and that then starts the oscillation process starting. So obviously we've got a resistor as well, and then on the high voltage output, once this multi-vibrator gets started and it's oscillating, this is the secondary side of a transformer, which is obviously a high voltage output, a step up, in other words, through a diode rectifier, across a capacitor, and then obviously via a potentiometer, which is what this device is here. That potentiometer then controls the voltage, obviously, to the socket of where the dosimeter connects. So it's a voltage control, really, that sets the needle on the dosimeter. So that's a little rundown of that. Well, fortunately, guys, I can't get this apart. The way you take this apart is by removing these thumb screws on the four corners, which should allow it to come out. But in order to get the case off, you've got to pull this off. You see, this has got to come off. Now, I've had pry bars under here and all sorts trying to get this off, and it's well and truly, it must be seized. You know, it's not held in with any, it's just push fit. So I think basically what's happened here is that with age it's just seized on. So I cannot get this off. I've tried all I can. As I say, I've had pry bars under it a lot. I don't want to damage it and break it, but it's just a wind up voltage actuator sort of thing that then does the same as what the other charger unit does. But yeah, it's just slightly different, that's all. This is an MOD, Ministry of Defence issue device, because it's got the MOD part number on it, etc. there, and the details of it. So, manufacturer. It's a shame really, I can't get into it. It is quite a large, what's in there? I'm not sure if we can see anything in there. Let's have a look. Oh, that's just for the, looks like just some internals that we can just see there, but that must be for the light for it. But yeah, I can't get into it, I'm afraid, so we'll have to leave that. We'll have to look at the radio now. As I say, I don't want to break it or damage it, so we'll move on to the radio. I think you get the idea. Okay, so we're coming to the end of the video now. Obviously we've had a look at the radio, we've had a look at the dosimeter, and the how to calibrate that. Obviously on the charger, we've looked at the charger units, how they're constructed, discussed a little bit about units of measure of radioactivity, and how to calculate the differences between sieverts, rads and greys, etc. There's quite a lot to it obviously now in the modern world as we see it, but back in the 1970s, 80s it was quite a blunt instrument was using one of these, because obviously you know, these were dosimeters over time, and naturally if you'd left it a bit long before looking at your dosimeter after a fallout cloud had settled in your area, and you know, you'd taken a bit long to read it and found out you got a fatal dose, it was too late, because normally radiation sickness occurred in the time which you get the sickness from the time the bomb went off is a time between contracting radiation sickness and dying, and they normally have that time relationship between each other. So radiation sickness was really something to be avoided, obviously, particularly of doses above a certain level. It was highly probable that you would pass away within a very short time, depending on the dosage. And you know, it's well documented now in many scientific books and things what the biological relationship is in humans and animals to certain doses of radiation, and therefore, you know, and obviously materials as well. From a civil defence perspective, in a nuclear bunker, bomb shelter, gamma rays can penetrate significant depths into reinforced concrete, and other materials pass through with ease over significant thicknesses of up to several feet in places. And then obviously the shorter, less energy radiation, such as alpha and beta particles, tend to get stopped with quite minimal thickness of materials or biological tissue. So again, there's lots of science behind it. That will be out the scope of this video. There are many publications that you can read and research on the internet to show about the different dosage levels of dosimeter applications and how that can affect your health in that kind of an environment. I think the truth is, of course, that after a nuclear war, certainly the civil defence exercises that took place in the 1980s, one of the more famous ones in the UK was Exercise Square Leg, or Operation Square Leg. That was a civil defence exercise. It was the last one actually before it was disbanded, and the information at the time coming out of the Soviets of their military scenarios with regard to attacking the West and NATO countries like the UK, for example, it was widely known and widely prophesied that each city in the UK or military target would receive at least 2 hydrogen bombs, a multi-megaton yield, and it's quite common knowledge that the Soviets have indicated that that would be the case, and likewise we would do the same to them. I mean, the city of Moscow would receive probably dozens of 1 megaton or higher yield thermonuclear weapons on it, and it will be totally destroyed to all imagination. But it's not hard to imagine that cities like Leeds and London and Bradford and Birmingham and Sheffield and Edinburgh and Glasgow and Manchester and Liverpool would all get multi warheads delivered on them, and some airburst, some ground burst, and it is hard to believe that there are nuclear war planners out there working on all sides, both our side, the Americans, the Soviets, and other countries as well in the world that are nuclear powers, that whose job is to actually look at how they can deform a structure or a target, and what kind of impact that they're wanting to inflict on the other side, and how many weapons and what yield they'll need to do that. And there's a lot of that being worked out, particularly in the Cold War era. Nuclear planners that would have had a weapon on every popsicle stand on the Trans-Siberian Highway if they could allow it. And of course the stockpiles between East and West were so enormous, thousands and thousands of missiles, ICBMs, on both sides. I think the British Trident sub carries 16 Trident intercontinental ballistic missiles, and each of those 16 missiles I think can take anywhere between 8 to 12, 16 warheads, and each warhead has a yield of over 1.2 megatons of thermonuclear hydrogen bomb, which is 1,000 times more powerful than both bombs dropped on Hiroshima and Nagasaki in the Second World War. I mean, the yield of I think the Nagasaki and Hiroshima bombs were about 20 kilotons in yield, equivalent to 20,000 tons of TNT, and they weren't thermonuclear either. So all you need to know about hydrogen bombs, or thermonuclear weapons as they're known, is that they use an atomic bomb as the initiator to get them going when they go off. So this is why these weapons are so powerful in modern day nuclear arsenals, that the idea of survivability after such an event is truly a joke, because a country as small as the UK would be absolutely reduced to a black smouldering pile of ashes, and Russia would be as well, and so would America. And there's just so many big bombs out there that would waste to such large expanses of land masses on both sides, and no doubt lead to a nuclear winter, as the hypothesis was back in the 1980s, that we could end up after a nuclear war having the entire civilization of the entire planet threatened by, even in countries that weren't hit with nuclear weapons, by a nuclear winter that would follow it, and there would be no survivors. The crops would fail, the food supplies would fail, everything would just literally be lost, and the world would perish. So it's it don't bear worth thinking about, really. So yeah, it's interesting times, back in that era. It's nice to see a bit of equipment and things from that day, and that the fact that we were all living at the time under the threat of nuclear annihilation, and thank goodness it never happened, and let's just hope it never does. So thank you for watching the video, and I'll catch up with you in the next. Goodbye. Okay, so we're coming to the end of the video now. Obviously we've had a look at the radio, we've had a look at the dosimeter, and the how to calibrate that, obviously on the charge. We've looked at the charge units, how they're constructed, discussed a little bit about units of measure of radioactivity, and how to calculate the differences between sieverts, rads and greys, etc. there's quite a lot to it, obviously, now in the modern world as we see it. But back in the 1970s, 80s, it was quite a blunt instrument was using one of these, because obviously, you know, these were dosimeters over time, and naturally, if you'd left it a bit long before looking at your dosimeter after a fallout cloud had settled in your area, and you know, you'd taken a bit long to read it and found out you got a fatal dose, it was too late, because normally radiation sickness occurred in the time which you get the sickness from the time the bomb went off is a time between contracting radiation sickness and dying, and they normally have that time relationship between each other. So radiation sickness was really something to be avoided, obviously, particularly of doses above a certain level. It was highly probable that you would pass away within a very short time, depending on the dosage. And you know, it's well documented now in many scientific books and things what the biological relationship is in humans and animals to certain doses of radiation, and therefore, you know, and obviously materials as well from a civil defence perspective. In a nuclear bunker, bomb shelter, gamma rays can penetrate significant depths into reinforced concrete, and other materials pass through with ease over significant thicknesses of up to several feet in places. And then obviously the shorter, less energy radiation, such as alpha and beta particles, tend to get stopped with quite minimal thickness of materials or biological tissue. So again, there's lots of science behind it. That will be out the scope of this video. There are many publications that you can read and research on the internet to show about the different dosage levels of dosimeter applications and how that can affect your health in that kind of an environment. I think the truth is, of course, that after a nuclear war, certainly the civil defence exercises that took place in the 1980s, one of the more famous ones in the UK was Exercise Square Leg, or Operation Square Leg. That was a civil defence exercise. It was the last one actually before it was disbanded, and the information at the time coming out of the Soviets of their military scenarios with regard to attacking the West and NATO countries like the UK, for example, it was widely known and widely prophesied that each city in the UK or military target would receive at least 2 hydrogen bombs of multi-megaton yield, and it's quite common knowledge that Soviets have indicated that that would be the case, and likewise we would do the same to them. I mean, the city of Moscow would receive probably dozens of 1 megaton or higher yield thermonuclear weapons on it, and it will be totally destroyed to all imagination. But it's not hard to imagine that cities like Leeds and London and Bradford and Birmingham and Sheffield and Edinburgh and Glasgow and Manchester and Liverpool would all get multi warheads delivered on them, and some airburst, some ground burst, and it is hard to believe that, you know, there are nuclear war planners out there working on all sides, both our side, the Americans, the Soviets, and other countries as well in the world that are nuclear powers, that whose job is to actually look at how they can deform a structure or a target, and what kind of impact that they're wanting to inflict on the other side, and how many weapons and what yield they'll need to do that. And there's a lot of that being worked out, particularly in the Cold War era. Nuclear planners that you know, would have had a weapon on every popsicle stand on the Trans-Siberian Highway if they could allow it. And of course the stockpiles between East and West were so enormous, thousands and thousands of missiles, ICBMs, on both sides. You know, I mean, I think the British Trident sub carries 16 Trident intercontinental ballistic missiles, and each of those 16 missiles, I think, can take anywhere between 8 to 12, 16 warheads, and each warhead has a yield of over 1.2 megatons of thermonuclear hydrogen bomb, which, you know, is 1,000 times more powerful than both bombs dropped on Hiroshima and Nagasaki in the Second World War. I mean, the yield of, I think the Nagasaki and Hiroshima bombs were about 20 kilotons in yield, equivalent to 20,000 tons of TNT. And they weren't thermonuclear either, you know. So all you need to know about hydrogen bombs, or thermonuclear weapons as they're known, is that they use an atomic bomb as the initiator to get them going when they go off. So this is why, you know, these weapons are so powerful in modern day nuclear arsenals that the idea of survivability after such an event is truly a joke, because, you know, a country as small as the UK would be absolutely reduced to a black smouldering pile of ashes, and Russia would be as well, and so would America. And you know, there's just so many big bombs out there that would waste to such large expanses of land masses on both sides, and no doubt lead to a nuclear winter, as the hypothesis was back in the 1980s, that you know, we could end up after a nuclear war having the entire civilization of the entire planet threatened by, even in countries that weren't hit with nuclear weapons, by a nuclear winter that would follow it, and there would be no survivors. The crops would fail, the food supplies would fail, everything would just literally be lost, and the world would perish. So, you know, it don't bear worth thinking about, really. So yeah, it's interesting times, you know, back in that era. It's nice to see a bit of equipment and things from that day, and that the fact that we were all living at the time under the threat of nuclear annihilation, and thank goodness it never happened, and let's just hope it never does. So thank you for watching the video, and I'll catch up with you in the next. Goodbye. So on the subject of dosage and what's particularly lethal or not lethal, I've got a useful reference book here, which actually I've had for quite some time. I think I picked this up from a second-hand shop many years ago when I was a kid, and interestingly it's forwarded by Dr. Edward Teller. Now, for those who don't know who Dr. Edward Teller is, he was the designer of the thermonuclear hydrogen bomb, which replaced the standard type of nuclear weapons that were detonated in Japan in the Second World War, the Hiroshima and Nagasaki weapons. He worked on the Manhattan Project along with Oppenheimer and the other key scientists. But Dr. Edward Teller furthered the nuclear science to develop the thermonuclear weapons. And thermonuclear weapons, all you need to know about those is that they make the bombs that dropped on Hiroshima and Nagasaki look like firecrackers in comparison to what's in the modern day arsenals of today. And indeed, hydrogen bombs, or thermonuclear weapons as they're known as, use a standard atomic bomb as the initiator to get them going. So that's all you need to know, really. So the destructive force of a hydrogen bomb, like for like in yield, is 1,000 times greater than a standard atomic bomb. So, you know, they're extremely life-ending, shall we say. Now, as far as radiation, radioactive fallout, etc. Is concerned, and its effects on the human body, I just wanted to expand on that, and I found a section in the book that talks about that. But what's interesting is knowing the effects of, when we looked at the dosimeter and its measurements of rantigens. So basically this measures rads, and we talked about earlier in the video the conversion factors between rads, grays, millisieverts or sieverts, and the types of damage that it can cause to humans. I just wanted to go into that a little bit further. Now it says here, it says for the vast majority who would receive radiation doses from a massive attack, the help of doctors, antibiotics, blood transfusions, etc., would not be of life or death importance. Very few of those receiving acute doses receive within 24 hours or less than 100 R would become sick. Even briefly, all those exposed to acute doses between 100 R and 200 R should recover from radiation effects. However, under post-attack conditions of multiple stresses, some who receive acute radiation doses of 100 R to 200 R may die of infectious diseases because of their reduced immunity or reduced resistance. If total doses this size or even several times larger are received over a period of a few months in small doses of around 6 R per day, no incapacitating symptoms should result. The human body usually can repair almost all radiation damage if the daily doses are not too large. The majority of those with acute doses of less than about 350 R will recover without medical treatment. Almost all those receiving acute doses over 600 R would die within a few weeks, even if they were to receive treatment in a typical hospital during peacetime. If all doctors and equipment and drugs needed for heroic treatments magically were to survive an attack, and persons suffering from radiation sickness would reach them, relatively few additional lives could be saved. The most effective way to reduce losses of health and life from radiation sickness is to prevent excessive exposure to radiation. Adequate shelter is essential. Life support items are the best means of saving lives in a nuclear war. Following information on radiation sickness is given to help the reader understand the importance of building a good shelter and to help diminish between symptoms and common illnesses and first symptoms of radiation sickness. So it says the first symptoms of radiation sickness are nausea, vomiting, headache, dizziness and general fatigue, I think. And it goes on to talk further about it, but basically it says that the symptoms begin several hours after exposure to acute doses of 100 R to 200 R, and within 30 minutes or less after receiving a fatal dose. A source of probable confusion is the fact that one or more of these symptoms is experienced by many people when they are first exposed to great danger. As in an air raid shelter during a conventional bombardment, the occupants of a shelter might worry unnecessarily for weeks, making their early emotional reactions to the initial phase of radiation sickness. This would be particularly true if they had no dependable instrument for measuring radiation, or if none of them knew how to use such an instrument. The initial symptoms end within a day or two, then follows the latent phase of radiation sickness, during which the patient experiences few, if any, symptoms. If the dose received was in the non-fatal range, the latent phase may last as long as 2 weeks. In the final phase, the victim of a serious or fatal radiation sickness will have reduced resistance to infections and is likely to suffer diarrhea, loss of hair and a small hemorrhages to the skin, mouth and or intestinal tract. Diarrhea from common causes may be confused with the onset of radiation sickness, but hemorrhages and loss of much hair are clear indications of having received serious but not necessarily fatal radiation exposure. The final phase usually lasts 1 to 2 months. Any available antibiotics should be reserved for this critical phase of the illness. Doses of 1,000 rads to 5,000 rads result in bloody diarrhea, fever and blood circulation abnormalities, with the initial symptoms beginning with less than 30 minutes after exposure and the final phase occurring less than a day thereafter. Death results within 2 to 14 days. The victim of a dose of over 5,000 rentgens dies a hard death within 48 hours due to radiation damage of a central nervous system. So basically, you know, doses of 1,000 rads or above, you've had it. That's basically what the book says, and you know, that's the way you've got to calculate with these. You see what dosage you've had over time, and that will then give you an idea of your exposure. Unfortunately, this dosimeter won't warn you if you're getting too high, but the modern electronic ones do. You can set alarm limits on them and things, and indeed people that deliver, well, people that go to the Chernobyl zone and explore there have modern radiation meters that do give alerts if a radiation level goes above a certain level. But obviously the radiation level around Chernobyl is far, far less, thousands and thousands of times lower than what an atomic bomb would give off immediately once the mushroom cloud has settled to the ground in the form of radioactive fallout. Now, obviously that's a little guide just to, you know, the seriousness of what these instruments, the role they would play after such a horrible event. But again, you know, only the fittest would survive, and no doubt, you know, the food that is harvested in crops and animals that graze the land, the radiation levels of, for example, the different iodines or whatever that affect the thyroid, such as, you know, cesium, strontium, and other radioactive elements that fall to the ground as fallout from the mushroom cloud, would inevitably cause ingestion of radioactive particles into the stomach when you're eating these foods, assuming, of course, you know, you can get food. So, you know, again, there's a lot of importance in the educational materials that civil defence people were trained in being able to recognise how to minimise radiation sickness or protect themselves from that for a certain period of time. And I suppose that's the emphasis, really, why there's such a big importance on food stocks, you know, keeping food stocks in your nuclear bomb shelter for up to 14 days after. Well, a minimum food stocks of 14 days because of the decay rate of radioactive fallout over that period once the hydrogen bombs have gone off and the mushroom clouds have been blown downwind and they eventually settle. Obviously gamma radiation is the one that penetrates the furthest into different materials, and there's guidance when you're building nuclear bomb shelters, for example, to have certain materials that surround the bomb shelter to try and absorb some of the gamma radiation. And there's quite a lot of guidance in these books that you can read that tells you about the types of depth in which, you know, certain types of rays will penetrate into what materials, and that's critically important. You know, that's why, you know, you have such a big mound of earth on top of bomb shelters and things as well, not just to protect against the concussion of the blast wave. And I think this is a good example of it here. I think this talks about such as the gamma ray, for example, 3 feet of earth, you see, absorbs gamma rays. So basically 999 gamma rays out of 1,000 get absorbed by 3 feet of earth. But obviously, you know, sky shine or scattered gamma rays, if you're not protected, can enter you. So yeah, it's quite interesting how these are looked at. But for 3 feet of earth, obviously if you didn't have that protective layer and you say had wood or other materials covering you, gamma rays could pass through it straight away with no problem. because there are certain materials which you know, would not protect you from gamma radiation, and of course that's the most damaging of the radioactive particles that can cause the most damage to human cells. So yeah, it's quite interesting how to do that. I was quite fortunate really many years ago that I used to go on courses at the Cabinet Office Emergency Planning College at Easingwold at York, which was the UK's Civil Defence College, and all the nuclear war planners and civil defence experts went there for training courses, including myself, on how to you know, deal with all the after effects of a nuclear attack. And indeed there was a lot of the air raid shelters that had been developed for the Second World War were actually designed there, and in the grounds of the Hawk Hills Emergency Planning College, out in the woods at the back, there are still the original Anderson shelters and the other types of air raid shelters that were designed there and then deployed across the country in the Second World War. And then obviously in the Cold War period, the nuclear function for civil defence was also developed there and progressed into what we see today, with a lot of knowledge and information that we've currently got in the world of academia for looking at the types of shelter and bomb shelter designs that people can build and indeed have done in some countries to protect from even some of the biggest hydrogen bombs that there are. So yes, there's a lot of information and things, but this book was quite a good one actually, from forwarded by Dr. Edward Teller, the nuclear physicist who designed the hydrogen bomb. I've got the feeling that Mr. Teller perhaps you know, didn't realise from what the information is contained in some of the notes that he made after the hydrogen bomb was first developed. I don't think he realised at the time, and indeed I think he's on record saying so, that basically you would I think he was a bit miffed as to how powerful the hydrogen bomb really was when it was tested, and I don't think that he realised just how what he'd designed really at first. I think he had an idea roughly up front, but I think when it was actually tested, I think he realised pretty soon it was a lot more powerful than he expected. Indeed, there were nuclear tests done on some of the Pacific islands where the yields were much greater than they'd actually calculated, and there was quite a few, well, one or two cases of a couple of things really, where the American personnel in a blast bunker on an island some 20 odd miles away from the initial explosion nearly died, because the explosion was way more powerful than they anticipated, and it nearly blew the bomb shelter away, and they also suffered severe radiation exposure. And then there was the case of the one, I think on Christmas Island, I think it was, or out in Bikini Atolls, where the yield of a weapon was far greater than calculated. And indeed, I think it was the Marshall Islands or somewhere out there, where it produced a radioactive fallout far in excess of what they thought, and it contaminated habited islands nearby, and I think there was some fishing fleets or something that got exposed to high levels of radiation, and some of them died, and they also had all the symptoms of radiation sickness that we just described in this book. So yeah, big stuff. So anyway, that at least gives you an idea of the level of radiation sickness that you know, that you could expect in that particular scenario, and how you would survive or not survive, as the case may be. So on the subject of dosage and what's particularly lethal or not lethal, I've got a useful reference book here, which actually I've had for quite some time. I think I picked this up from a second-hand shop many years ago when I was a kid, and interestingly it's forwarded by Dr. Edward Teller. Now, for those who don't know who Dr. Edward Teller is, he was the designer of the thermonuclear hydrogen bomb, which replaced the standard type of nuclear weapons that were detonated in Japan in the Second World War, the Hiroshima and Nagasaki weapons. He worked on the Manhattan Project along with Oppenheimer and the other key scientists. But Dr. Edward Teller furthered the nuclear science to develop the thermonuclear weapons. And thermonuclear weapons, all you need to know about those is that they make the bombs that dropped on Hiroshima and Nagasaki look like firecrackers in comparison to what's in the modern day arsenals of today. And indeed, hydrogen bombs, or thermonuclear weapons as they're known as, use a standard atomic bomb as the initiator to get them going. So that's all you need to know, really. So the destructive force of a hydrogen bomb, like for like in yield, is 1,000 times greater than a standard atomic bomb. So, you know, they're extremely life-ending, shall we say. Now, as far as radiation, radioactive fallout, etc. Is concerned, and its effects on the human body, I just wanted to expand on that, and I found a section in the book that talks about that. But what's interesting is knowing the effects of, when we looked at the dosimeter and its measurements of rantigens. So basically this measures rads. And we talked about earlier in the video the conversion factors between rads, grays, millisieverts or sieverts, and the types of damage that it can cause to humans. I just wanted to go into that a little bit further. Now, it says here, it says for the vast majority who would receive radiation doses from a massive attack, the help of doctors, antibiotics, blood transfusions, etc. would not be of life or death importance. Very few of those receiving acute doses receive within 24 hours or less than 100 hours would become sick. Even briefly, all those exposed to acute doses between 100 hours and 200 hours should recover from radiation effects. However, under post-attack conditions of multiple stresses, some who receive acute radiation doses of 100 hours to 200 hours may die of infectious diseases because of their reduced immunity or reduced resistance. If total doses this size or even several times larger are received over a period of a few months in small doses of around 6 hours per day, no incapacitating symptoms should result. The human body usually can repair almost all radiation damage if the daily doses are not too large. The majority of those with acute doses of less than about 350 hours will recover without medical treatment. Almost all those receiving acute doses over 600 hours would die within a few weeks, even if they were to receive treatment in a typical hospital during peacetime. If all doctors and equipment and drugs needed for heroic treatments magically were to survive an attack, and persons suffering from radiation sickness would reach them, relatively few additional lives could be saved. The most effective way to reduce losses of health and life from radiation sickness is to prevent excessive exposure to radiation. Adequate shelter is essential. Life support items are the best means of saving lives in a nuclear war. Following information on radiation sickness is given to help the reader understand the importance of building a good shelter and to help diminish between symptoms and common illnesses and first symptoms of radiation sickness. So it says the first symptoms of radiation sickness are nausea, vomiting, headache, dizziness and general fatigue, I think. And it goes on to talk further about it, but basically it says that the symptoms begin several hours after exposure to acute doses of 100 hours to 200 hours, and within 30 minutes or less after receiving a fatal dose A source of probable confusion is the fact that one or more of these symptoms is experienced by many people when they are first exposed to great danger. As in an air raid shelter during conventional bombardment, the occupants of a shelter might worry unnecessarily for weeks, making their early emotional reactions to the initial phase of radiation sickness. This would be particularly true if they had no dependable instrument for measuring radiation, or if none of them knew how to use such an instrument. The initial symptoms end within a day or two, then follows the latent phase of radiation sickness, during which the patient experiences few, if any, symptoms. If the dose received was in the non-fatal range, the latent phase may last as long as 2 weeks. In the final phase, the victim of a serious or fatal radiation sickness will have reduced resistance to infections and is likely to suffer diarrhea, loss of hair, and a small hemorrhages to the skin, mouth, and/or intestinal tract. Diarrhea from common causes may be confused with the onset of radiation sickness, but hemorrhages and loss of much hair are clear indications of having received serious but not necessarily fatal radiation exposure. The final phase usually lasts 1 to 2 months. Any available antibiotics should be reserved for this critical phase of the illness. Doses of 1,000 rads to 5,000 rads result in bloody diarrhea, fever, and blood circulation abnormalities, with the initial symptoms beginning with less than 30 minutes after exposure and the final phase occurring less than a day thereafter. Death results within 2 to 14 days. The victim of a dose of over 5,000 rentgens dies a hard death within 48 hours due to radiation damage of a central nervous system. So basically, doses of 1,000 rads or above, you've had it. That's basically what the book says, and that's the way you've got to calculate with these. You see what dosage you've had over time, and that will then give you an idea of your exposure. Unfortunately, this dosimeter won't warn you if you're getting too high, but the modern electronic ones do. You can set alarm limits on them and things, and indeed people that go to the Chernobyl zone and explore there have modern radiation meters that do give alerts if a radiation level goes above a certain level. But obviously the radiation level around Chernobyl is far, far less, thousands and thousands of times lower than what an atomic bomb would give off immediately once the mushroom cloud has settled to the ground in the form of radioactive fallout. Now, obviously that's a little guide just to the seriousness of what these instruments, the role they would play after such a horrible event. But again, only the fittest would survive, and no doubt the food that is harvested in crops and animals that graze the land, the radiation levels of for example the different iodines or whatever that affect the thyroid, such as cesium, strontium, and other radioactive elements that fall to the ground as fallout from the mushroom cloud, would inevitably cause ingestion of radioactive particles into the stomach when you're eating these foods, assuming of course you can get food. So again, there's a lot of importance in the educational materials that civil defence people were trained in being able to recognise how to minimise radiation sickness or protect themselves from that for a certain period of time. And I suppose that's the emphasis really, why there's such a big importance on food stocks, keeping food stocks in your nuclear bomb shelter for up to 14 days after. Well, minimum food stocks of 14 days because of the decay rate of radioactive fallout over that period once the hydrogen bombs have gone off and the mushroom clouds have been blown downwind and they eventually settle. Obviously gamma radiation is the one that penetrates the furthest into different materials, and there's guidance when you're building nuclear bomb shelters, for example, to have certain materials that surround the bomb shelter to try and absorb some of the gamma radiation. And there's quite a lot of guidance in these books that you can read that tells you about the types of depth in which, you know, certain types of rays will penetrate into what materials, and that's critically important. You know, that's why you have such a big mound of earth on top of bomb shelters and things as well, not just to protect against the concussion of the blast wave. And I think this is a good example of it here. I think this talks about such as the gamma ray, for example. 3 feet of earth, you see, absorbs gamma rays. So basically 999 gamma rays out of 1,000 get absorbed by 3 feet of earth. But obviously, you know, sky shine or scattered gamma rays, if you're not protected, can enter you. So yeah, it's quite interesting how these are looked at. But for 3 feet of earth, obviously if you didn't have that protective layer and you say had wood or other materials covering you, gamma rays could pass through it straight away with no problem. Because there are certain materials which you know, would not protect you from gamma radiation, and of course that's the most damaging of the radioactive particles that can cause the most damage to human cells. So yeah, it's quite interesting how to do that. I was quite fortunate really many years ago that I used to go on courses at the Cabinet Office Emergency Planning College at Easingwold at York, which was the UK's Civil Defence College, and all the nuclear war planners and civil defence experts went there for training courses, including myself, on how to you know, deal with all the after effects of a nuclear attack. And indeed there was a lot of the air raid shelters that had been developed for the Second World War were actually designed there, and in the grounds of the Hawk Hills Emergency Planning College out in the woods at the back, there are still the original Anderson shelters and the other types of air raid shelters that were designed there and then deployed across the country in the Second World War. And then obviously in the Cold War period, the nuclear function for civil defence was also developed there and progressed into what we see today, with a lot of knowledge and information that we've currently got in the world of academia for looking at the types of shelter and bomb shelter designs that people can build and indeed have done in some countries to protect from even some of the biggest hydrogen bombs that there are. So yes, there's a lot of information and things, but this book was quite a good one actually, from forwarded by Dr. Edward Teller, the nuclear physicist who designed the hydrogen bomb. I've got the feeling that Mr. Teller perhaps you know, didn't realise from what the information is contained in some of the notes that he made after the hydrogen bomb was first developed. I don't think he realised at the time, and indeed I think he's on record saying so, that basically you would I think he was a bit miffed as to how powerful the hydrogen bomb really was when it was tested, and I don't think that he realised just how what he'd designed really at first. I think he had an idea roughly up front, but I think when it was actually tested, I think he realised pretty soon it was a lot more powerful than he expected. Indeed, there were nuclear tests done on some of the Pacific islands where the yields were much greater than they'd actually calculated, and there was quite a few, well, 1 or 2 cases of a couple of things really, where the American personnel in a blast bunker on an island some 20 odd miles away from the initial explosion nearly died, because the explosion was way more powerful than they anticipated, and it nearly blew the bomb shelter away, and they also suffered severe radiation exposure. And then there was the case of the one, I think, on Christmas Island, I think it was, or out in Bikini Atolls, where the yield of a weapon was far greater than calculated. And it, indeed, I think it was the Marshall Islands or somewhere out there, where it produced a radioactive fallout far in excess of what they thought, and it contaminated habited islands nearby, and I think there was some fishing fleets or something that got exposed to high levels of radiation, and some of them died, and they also had all the symptoms of radiation sickness that we just described in this book. So yeah, big stuff. So anyway, that at least gives you an idea of a level of radiation sickness that you know, that you could expect in that particular scenario, and how you would survive or not survive as a